There is a hidden kind of gravity in statistics. You can start with data that looks like a slide, a solid block, or even a camel's back. It doesn't matter. Individual values can swing wildly. But everything changes when we start grouping them. Imagine we split that messy data into equal-sized groups. We calculate the average for every single group, and we plot those averages on a histogram. Now, watch what happens if we increase the size of those groups. With small groups, the histogram might still look a bit messy, but as we make the groups bigger and bigger and replot their averages, the shape starts to change. The averages become stable, and as that group size grows, that hidden gravity takes hold. It pulls those averages toward the center, collapsing the mess into the same perfect shape. The normal distribution. And the law that makes this happen? That is the Central Limit Theorem. Okay, that was the magic trick. But you might have noticed I left the labels off the axes. I didn't tell you what we were measuring. That was deliberate. I wanted you to feel the gravity before we looked at the maths. Now, let's slow it down. Let's see exactly how that pile of averages builds up. Here is our messy population on the left, a log normal distribution, the kind of shape you see in income, reaction times, or stock returns. Decidedly not normal. On the right, we're going to build a new distribution. But instead of raw values, we're plotting averages. Let's start with n equals 1. If we just pick single values, one at a time, thousands of times, see, exactly the same shape. No surprise there. Each average is just that one value. Now let's try n equals 2. We pick two values, average them, plot that, and repeat. Already, something is happening. Look at the ghost of the previous distribution behind it. N equals 5, n equals 10, n equals 20. With each increase, the pile gets narrower, taller in the middle. The skew is fading. N equals 30, n equals 100. That messy log normal shape has become something remarkably symmetric. We didn't draw a bell curve. The bell curve emerged, naturally, from the simple act of averaging. So why does taking the average do this? Why does averaging calm the chaos? In the original population, you have extreme values, very high and very low. Pick one value at random and you might hit an extreme. But pick a whole handful, then take the average, and it's very unlikely the entire handful is extreme. A handful usually contains a mix, highs, lows, and middle values. When you take the average of a mix, the result gets pulled back toward the center. That's why these averages cluster tightly. Averages are harder to push to extremes than individual values. So we understand the mechanism, but for your exams, why do we actually care? Real-world data is often not normal. Waiting times, prices, durations, they can be skewed or uneven. And it's not that we can't work with those shapes. We can, if we know the exact model. But each different shape needs its own assumptions, its own formulas, its own methods. The normal distribution is special because it is mathematically well behaved. It's smooth, symmetric, fully described by just a mean and a spread. It's a bit like how linear models are easier to analyze than complicated nonlinear ones. Not the only thing you can use, but incredibly powerful and flexible. And most of the core tools of statistical inference, test statistics, and confidence intervals are built around normal behavior. We'll explore those properly later in this series. And here's the breakthrough. Even when the original population is not normal, the averages of large samples are approximately normal. So by working with sample averages, we unlock all those powerful inference tools without needing the population itself to be normal. The Central Limit Theorem lets you reach the normal world by averaging your way there.